This is just going to be a quick reteach of the graphing, cosecant, and secant lessons. I'm not going to really write much on the screen, just kind of talk through the parts of the notes that are important. So the cosecant function is the reciprocal of sine, or that's what we learned when we went over the trig functions. And since it's the reciprocal, we can take the table that we made last class for sine of x and just use the reciprocal of all of these output values, reciprocal being the flipped fraction, right? So if you use the reciprocal of 0, well, that would be 1 over 0, and you can't divide by 0, so that's an undefined moment for us. And we just do the reciprocal of all the other values here on the table. So from 0 to 2 pi, all of the values for cosecant would be pi over 6 comma 2, 0 comma undefined, so there's a gap here in the graph called a vertical asymptote. Then we have pi over 6 comma 2, pi over 2 comma 1, 5 pi over 6 comma 2, and then another vertical asymptote. And you can see the other part of the period is here. So again, from 0 to 2 pi, one period of the cosecant function looks like this in green. Okay, it's not on our table, but we can kind of make a good little assumption of what it looks like from negative 2 pi to 0, which would just be the same period repeated over those values. Now, some important things about cosecant: its period is still 2 pi. So from 0 to 2 pi, you get one full wave of the cosecant, just like its sine, the inverse of it, reciprocal. The amplitude is still the distance from the center line to the max or min values, because the max or min value of what sine was is the same for cosecant. Get my words all crazy. So the domain of the cosecant function is all real numbers except for multiple values of pi, because at all of pi, 2 pi, negative pi, and negative 2 pi, and 0, so multiples of pi, then you have a vertical asymptote there, so our domain is undefined. And our range is just the reciprocal of the sine curve's range. So the sine curve went from negative 1 to 1. So the cosecant range is literally everything else, from negative infinity all the way to negative 1. Pick up your pencil, start again at 1 all the way to infinity. We have vertical asymptotes at the values x equals, remember, because it's a vertical line, it's a Vux line, at 0 and at every multiple of pi after that. And just like its reciprocal sign, cosecant is an odd function, which means it's reciprocal. Wow, now I'm not even saying the right words at all. It is symmetrical about the origin. Last little facts that we need to know about cosecant is another sort of ways that it's related to sine. So cosecant has vertical asymptotes at the zeros of sine. It has local minimums at each of the local maximums of sine. And it has local maximums at each local minimum of sine. Which makes sense. If you look back at the graph on the other side, anywhere that the sine curve touched the center line, the x-axis for this one, there was a vertical asymptote for my cosecant that we drew in. So this is really important information for us, especially when it comes time to graph cosecant, because we can always graph sine and know where the vertical asymptotes and local maxes and mins for cosecant are, which is very helpful in graphing. We can do the same thing for the secant function. Secant is the reciprocal of the cosine function, so same thing as with sine. Here's the cosine table, and we're just going to take the reciprocal of all of those values, flip over the fraction, and we get our values for cosine. Okay, we've graphed this here along with the vertical asymptotes everywhere the graph is undefined. And we can talk about secant's values. So secant still has a period of 2 pi. We start at a maximum or a minimum here for secant. Okay, it's the maximum for cosine, so it's a minimum for secant. And we go up, hit a vertical asymptote, jump back down, finish this curve off. Oh, another vertical asymptote, come back down. Okay, that is one period of the secant function. Its amplitude is still 1 for the parent function because the distance from the center line to the max or min is still just 1. And the domain here is all real numbers except 2k plus pi k. Vertical asymptotes at the same values, but it's x equals because x equals is a Vux line. And this one is also symmetrical about the y-axis, just like cosine is, which makes sense since they're reciprocals. Now secant, again, is very similar to what we just talked about with sine and cosecant. So cosine and secant are related. Secant has vertical asymptotes everywhere that zeros of cosine exist. Secant has a local minimum at each local maximum of cosine, and secant has local maximums at each local minimum, which again you can verify on the graph that we put in our notes. Now last but not least, we can talk about the transformations of secant and cosecant, but what's nice is it's the same vocabulary. Remember that numbers multiplied in the very front, we would have called them vertical stretches and shrinks and some of our reflections over the x-axis when we were talking about transformations, but with sine waves, cosine waves, and thus secant and cosecant, we call that the amplitude. That's the distance from the center line to the top or bottom of the wave. The period is not b, so don't get it twisted. Don't say b is the period. B helps us find the period. Okay, the period is how long it takes for that function to repeat. It helps us talk about the frequency of the curves. And the formula for period is 2 pi over b. C talks about phase shifts. This would be our horizontal translations left and right. That's a phase shift. It affects where we're starting our wave. Normally sine and this cosecant start at 0 at the origin, and secant and cosine begin at 1, but this might be shifted left or right. Displacement also helps us shift the graph vertically up and down, but it's called displacement, and it affects the center line. Now this is really important. If your center line moves off of the x-axis, so if you have a displacement in your waves, then all of your zeros, I'm using air quotes, you can't see me do this, all of your zeros are now just places where the curve crosses the center line. So even if I notice that my graph is off, I'm trying to get my marker to work here, and we're just going to, so even if that's my normal x-axis, if I have a displacement that starts here and that's where my wave comes through, all of the places that I'm going to have a vertical asymptote are not where the graph cross the x-axis. It's a horrible graph. It's going to be where it crosses the center line. That's where, man, I kind of missed a little bit. That's where all of the vertical asymptotes are. So it's not necessarily always the zeros of the function if there's a displacement. It's where it's crossing the center line, which would be 0, but we've shifted it up. So it's a really important note to make. The reason that we want to make all these connections between cosecant and sine and secant and cosine is because it's easier to graph secant and cosecant if you begin by graphing their reciprocals first, because all of the amplitude, phase shift, period, and displacement is going to be the same for both the reciprocal and secant or cosecant. So we have to know how to graph sine and cosine before we can graph secant and cosecant.